In this video, we're going to be taking a look at 1.2, scaling up and down. We have looked at previously, we've looked at these things called scale drawings, which we talked about were like blueprints. When you have the blueprints of a house, that is a scale drawing of the house. And then also the idea that what it means for shapes to be similar, meaning they are the same shape, they're just different sizes. So if you don't have that written down in your notes, make sure you write that down. Similar means same shape, different size. Today, in this video, we are going to be looking at corresponding sides and corresponding angles. If you don't already, go ahead and copy this down in your notes exactly as it is, and then we're going to talk about it. Okay, so let's talk about it. Corresponding angles. Since corresponding angles are always the same, meaning if they are corresponding, they are the same angles, so the same measurements. If you enlarge an image like we did with our rubber band experiment, the angles remained the same. So to show angles are the same in mathematics, we use something like a semicircle. So for example, A and D are the same. And then to show B and E, we would use two semicircles, Wi-Fi marks, whatever you want to call them. And to show C and F are the same, you would use 1, 2, you guessed it, 3 of those markings. So looking at these marks, we know that A and D are the same. They are corresponding. B and E are the same. C and F are the same angles. Now, the same is not true for corresponding sides, meaning corresponding sides are going to be different in lengths. However, for example, if you look at BA and ED, those are corresponding sides, meaning that is the same side, only it's proportionally larger than BA. So ED is similar to BA. And we're going to look at the relationship between those sides. Also, the other sides, if you have EF, that is similar to BC. And then lastly, AC and DF are similar. So in your notes, make sure you use different colors to represent the similar sides or the corresponding sides. Make sure you have definitions also for corresponding angles. Remember, they are the same size, and corresponding sides, they are sides that are similar to each other. Now, moving forward, I do not want you to write angles like they have here. This is how I want you to write angles. So if you look at the small triangle, okay, we are looking, let's do this in the color purple. Okay, we're looking at this angle right here. There's different ways to write that. So instead of just B, you are going to do angle, so a little slanted L that represents mathematically angle. And you are going to write angle A, B, C. So it goes A from B, from A to B to C. So from A to B to C. And you notice B is your middle letter. That's very important. B is your middle letter. Okay. Then to show, another way to show angle B is to write then C, B, A, where B is still your middle letter. So those are two ways to show angle B. If we show angle A, let's do this in a different color. So let's do this in whatever color this is. So angle A, angle B, A, C, or angle C, A, B. Again, A is your middle letter. Those are two different ways to show angle A. And then lastly, let's go ahead and look at angle C. Angle B, C, A, or angle A, C, B. You notice C is your middle letter. Those are two different ways to show angle B. So we are not writing it like this anymore, right? I want you to write them like this. And the reason being is in the more advanced mathematics courses and textbooks that you'll use, you will see them written like this, 9.9 times out of 10. Okay, so we have to get used to writing them like that. Go ahead and write the angles of the large triangle over in this space here. Pause the video, write those angles, and see what you got. Go ahead and check your answers here to see how you did. You should have for angle E, either one of those. For angle D, either one of those. And for angle F, either one of those. All right, so that's what all of this says as to how to rewrite them. Again, I want you to write them like this, not so much like that. Okay, so now let's take a look at setting up our big story, getting back into our story of trying to figure out who that teacher is, right? So now we have this thing called, this is our super sleuth, right? This is our detective, this triangle dude or lady with a hat. That is our super sleuth. So now what we want to do, what Daphne wants to do, she wants to, here's the original. She wants to either enlarge it or reduce it, right? So you're copying it at different percentages, either larger, or if it's at a percentage less than 100%, it is smaller. Okay, so that's the whole idea, and that's what we're doing, and we're answering questions like, hey, how are these similar, in what ways, or what factors are they similar by? Let's go ahead and answer these questions. Go ahead and try A on your own. So try this one, A, 1 through 4 on your own. Pause the video, come back, and see how you did. So for the first one, where it says describe how the side lengths compare, up here, the side lengths. So again, we're comparing, for example, these side lengths are all corresponding right there. So if we look at those side lengths, and then we have these corresponding side lengths here, and then lastly we have those corresponding side lengths there. Now, if you go from the original to, let's do this one, let's do the original from here to there, right, to the 75%, those side lengths are all smaller, but they're smaller by a factor of 3/4. So if, for example, if you knew that this was 12, this here would be 3/4 times 12. Okay? And so it's that much smaller. And then if you wanted to 3/4 times 12, that would be then 9. So it's 75% the size of the original. Okay, so you have to explain that. And then now if you go from here to the larger one at 150%, if this was 12, 150% is 1.5 or 3/2, either one of those. You would take 12 times 1.5 or 12 times 3/2, which then gives you 18. So this new one now, if the original was 12 inches long, the new one would be 18, and the one at 3/4 would be 9 inches. Okay, so you have to answer that question saying not only it's larger, but it's this much larger. So 1.5 times larger or 3/4 smaller. Okay, now describe how the angle measures. Go back here. Compare. Now remember, we learned at the beginning of this video that the angle measures, the corresponding angles are always the same. So this angle right here and that angle right there and that angle right there are all corresponding. They are the same. This angle, and this angle, they are all corresponding. Therefore, they are the same. This angle, this angle, and this angle. Those are all corresponding, therefore they are the same. So that answers number 2. And then number 3 says describe how the perimeter of the triangles compare. Now listen, this is easy one, because if your lengths, for example, from the original to the one that's copied, if your lengths are 150% larger, meaning 1.5 times larger, the perimeter is also going to be 1.5 times larger. Okay, because each side length is added together to get the perimeter. And so then down here, since that is 3/4 times the size, meaning it's smaller, then the perimeter is going to be 75% smaller, or 3/4 or 0.75 times larger, or smaller, sorry, 0.75 times smaller than the original. All right, so the perimeter is going to be 75% the size. So the perimeter and side lengths are tied together in that way. Area is going to be a little bit different. And now if we look at the areas of these things, so on the last question, describe how the area, right? We're going to study the area quite a bit more, but for this one, if you go ahead and just throw some arbitrary numbers in there, so like let's say that this is 10 and 8, then you can figure out, well, what are the other ones going to be? Well, then this is going to be 15 and 12, right? And if you find the areas of this triangle, remember the area of a triangle is 1/2 base times height. So it's going to be half of, in this case, 8 times 10, which is 40, and then half of 12 times 15. So if we look at this, this has an area of 40. Right, because 8 times 10 is 80, half of that is 40, and this other one has an area of, if you take the base times the height, so that's 15 times 12 divided by 2, that'd be like 15 times 6, which is 90. So this is 90 units squared. There we go, gotta squeeze it in there. And so if you notice, even though the side lengths are 1.5 times more, the area, look at this, it goes from 40 to 90. The area is more than 200%. So the area is more than 200%. So it more than doubled. So the area is not the same. It does not change at the same rate at which the side lengths or the perimeter do. So the area is very different. And down here, if you went ahead and did your side lengths here, so let's say if this was 12 and 3/4 of 10 and then 3/4 of 8. So 3/4 of 10 on this one right here, that's 7.5. 3/4 of 8 is 6, and the area is the base times the height. So the area of this triangle is going to be 6 times 7.5 over 2. And we can use some of our properties from before to simplify here. You have 1 and 2 goes into 6 3 times. So you would have just 3 times 7.5, which is 22. So let me write this in here. 22.5 units squared. All right, so now if you look at the area of the small one, and again, we just made up these numbers, but the numbers, it doesn't matter. This gives us a good idea of what how those areas are related. You notice that the area at 3/4 is just over half. And so the area got much smaller. It didn't get smaller by a rate of 75%. It got much, much smaller than that. Just like the area when you multiply it by 1.5 or 150%, the area more than doubled. So the area is not tied to the same relationship as the perimeter and side lengths have. That's very important. If you need to pause the video, digest that, and write about it in your math notes. Now let's take a look at B. How do the relationships and the size comparisons you made in question A relate to the copier size factors used? So we've answered that quite a bit actually in the work that we just did. But really what this question is getting at is the idea that you have to understand that 75% is the same as 0.75 is the same as 3/4. So that is your what's called your scale factor. And we're going to learn a lot more about that in this unit. But in order to find your new side lengths like we did up here, you would multiply in this one right here, you would multiply all of the original side lengths, which again, I just made up 12, 10, and 8. They are arbitrary. I just made those up. You would multiply those by the scale factor of 75%, which is 0.75, or we know that is 3/4 as a fraction. For 150%, I'm going to do it down here. For 150%, that is a decimal of 1.5, which is the same as 3/2. Now I use fractions quite a bit because when you're using fractions, like when you multiply these by 3/2, a lot of times it makes it a lot easier. For example, down here, the 12 and 2 will simplify to 1 and 6. If you needed to multiply each of those by 3/2, multiplying by 1.5, you'll need a calculator, but a lot of times we won't have it. So changing them to decimals and then fractions will make the math aspect of this a lot easier. So that's what B is getting at, the idea that percents can change into decimals or fractions. And then let's take a look at part C. On number 1, if two figures are similar, what is the same? What is the same about the figures and what is different? And number 2, if you wanted to achieve a 100%, a 150% increase with the rubber band method, what would you do? Go ahead and try to answer these on your own. Pause the video, answer them on your own, and then come back. Okay, on the first one, if two figures are similar, what's the same about the figures? So the thing that's going to be the same, we've said this a couple times already, those are the angles. Those are always going to be the same on corresponding or similar figures, okay? What's going to be different? So what's going to be different? The area is going to be different, okay? And that's going to be changed by a factor that we don't know how to find yet. We know, though, it's going to change by a factor that's different than in this case, we gave 150% or 75%. It's going to be different than that. The perimeter and side lengths are going to change by the factor that's given, in this case 150% and 75%. So those are the three things that are going to change. Perimeter and side length change the same as the given factor, the change factor, scale factor, and then the area going to change differently. Number 2, if you wanted to achieve a 150% increase with the rubber band method, what would you do? So this is kind of fun. You can try this at home. You're going to need 3 rubber bands. So rubber band 1, rubber band 2, rubber band 3. And they're all connected, so I'm going to put my little knots here, right? So if you want a 150% increase, you are going to use that knot right there to trace your original figure. Okay, so that's at 150% increase. You're going to use that second knot there. If you wanted then it to be 300% right there, you're going to use this knot. Okay, you're going to use that knot. So this is a 3:2 ratio. This is a 3:1 ratio. If you're going to use those different knots. I know it didn't ask you that, but that's how those rubber bands work. Like if you had 2 rubber bands, 1, 2, right? That is a 2:1 ratio, which would be 200%, or it doubled it. And that's most likely what you did in class or at home. And that is it for this section right here. And in fact, that's it for this investigation. After this investigation will be the quiz for both 1.1 and 1.2. So make sure you are ready for that.